the 111 iron nickelite, lithium iron phosphide, lithium iron arsenide. And I'm going to do that. First, I'm going to give a short motivation on why we chose the 111 materials and why doing quantum oscillations. Then I'm going to give a short introduction to what the DHBA effect actually is, where does it come from, what did we learn from it, and then I'll show some results and what we can conclude from that. The work has been done mainly between our group and Bristol, my supervisor Tony Carrington, and Silva Famaglia Claudia in Oxford, and we had many inputs from others, group in Kyoto, group samples for us, measurements with untitled field that goes to zeros and 9A, and with the theory we had very help from Nico Massey. So what is our motivation to actually study this material? So we would like to understand, is there a link between the appearance of superconductivity in the nictilites and a certain change in the Fermi surface, appearance of pockets, change of pocket warpings, things like that. And how does the effective mass of different bands actually change when superconductivity appears? So things, or why we chose the lithium iron phosphide arsenide samples is because they're very unique to do that actually. Because if you want to observe quantum oscillations, you need very, very pure samples, and any sample that is doped, basically the dopant reacts as scattering in your sample. So lithium iron arsenide, lithium iron phosphide do not need to dope. They're both superconducting in stoichiometric form. And in addition to that, the end members on each side, lithium ion arsenide shows no nodes on the superconducting gap, while lithium ion phosphide shows nodes on the superconducting gap. So the main features that would be interesting for probing theories are basically common in those materials.
So on which experimental probes do you establish the nodes?
They have been shown by Ken Hashimoto recently in arXiv, and they were measured by penetration of measurements on the same samples from the same batch that we use to do quantum oscillations. So how do we do that? We use the Haas-von-Alphen effect, which is observing quantum oscillations in the mechanization. And the way we get that is when we apply magnetic field to a Fermi liquid, we get Landau tubes in K-space. And they basically, if we pop that up and we look at the density of states and how they change on the Fermi level, then what we get is that if we increase the field, our Landau levels grow to the Fermi surface. And as they go to the Fermi surface, we get an oscillation of the density of states at the Fermi level. And this can be seen in peak capacity, resistivity, and we see it in mechanization. So how do we describe that? There's a LiFeAs dosage formula, which I sketch out here, the main factors of that, which describes how we interpret the data that we get. We have this oscillatory part, which we learn is oscillating with a certain frequency in 1 over E space and not directly in D. And the amplitude of this is modulated or damped by two main factors. There can be a lot more depending on your system. But the two main factors are the temperature damping part, which we can extract the effective mass of the quasi-particles from by keeping the field constant and changing the temperature. Or we can learn something about our mean free path by looking at a constant temperature and just looking at how the amplitude basically changes the field. Okay, what we can learn from that first of all is what is the interaction due to the quasi-particle mass, and what's the mean free path, so how good is our sample. But what we would also like to know is how does the Fermi surface change, or how does it look like in three-dimensional. So what I draw out here are basically a two-dimensional, perfectly two-dimensional cylindrical Fermi surface. And if we do those measurements and we change the angle of those, so we change the field, then we basically prove a different extremal orbit. And if we plot the frequency that we observe times cosine of theta, we basically just get a straight line. So this would be perfectly two-dimensional. And now if we do the same thing with a Fermi surface that's slightly warped in Kz, then again, we do not have this perfectly cylindrical shape. So what we see is a deviation from this straight line that we had on the other side. And for minimal orbit, we basically get an upturn in the frequency times cosine theta, and for maximal, we get a downturn. So this is what we basically would look like in terms of how does our frequency change with angle. Now, how do we measure that? Measurements can be taken very clean crystals in low magnetic fields up to 20 Tesla. For the materials we looked at, especially the lithium-ion arsenide, of having critical fields of up to 15 Tesla, we had to go to pulse field facilities or high magnetic field facility 9A up to 32 Tesla. And in the 32 Tesla, it's rather easy to observe because you can sweep very slowly and you have good signal to noise. In 58 Tesla, this is pulse magnetic field, and you can see the whole experiment takes place in about 0.5 seconds. And how we do that is we use an AFM microcantilever, and we measure the resistance change of this that we get due to a torque. So this is magnetization times field. We get the torque, so we get bending in this lever, and we measure the resistance change of this compared to a reference. So we're only staying left with what our sample gives us, and to give you an impression of how big that is, so this is 50 by 100 micrometer. And if we do that, we get, even for pulse field, very, very clean data. So the guys in Toulouse did a great job there. So in the lithium iron phosphide, we have a small background, and we can see it clearly by the oscillations involved. The lithium iron arsenide, we have the superconducting part, and then we have a very big background, which is also due to the fact that the lithium iron arsenide samples we studied are about a factor 4 to 5 bigger. But slightly up here, we can see oscillations. And now we would like to learn something out of that. So we go to the Lifshitz-Kozlovich formula, but that only tells us something about the oscillation part. So the magnetic background, which do whatever that is not included there. So we have to subtract the fourth order polynomial in that case to basically get rid of this background, and then we stay left with the oscillations that we can actually study. And the way we do that is we look again, where is it oscillating? It's oscillating in 1 over B. So we go in the inverse B space and do an FT there. And then we actually end up with something that we can, well, that we actually were looking for. So we need the information on the amplitude that we get by the height of the peak, and we actually look at the frequencies of those peaks. And we can see in the lithium-ion arsenide, we can observe 3 peaks from the FFT, and in the lithium-ion phosphide, we have 2 peaks at the front, then we have 1 peak, which is the second harmonic of those mix, and then we have 4 additional peaks. So, like I said, we want to learn something about the many-body interaction. So we go to this temperature damping term, and we plot the amplitudes that we get from the pulses at different temperatures versus the temperature, and then we get basically those points here and can fit that with that formalism. And what you can easily see by in the beginning is that the lithium-ion phosphide rather has flat decrease of amplitude, while the lithium-ion arsenide is falling quite fast. And what that tells us already from those pictures is the lithium-ion arsenide will have higher many-body effective masses than the lithium-ion phosphide will. And I'll come back to that in a bit. I'll show you the other variable, and that is the angle. So if we change the angle and then look at the FFTs, we actually get different points. So we vary the frequency. And if we recall from the introduction, what we basically look for is this would be a maximum in warping, and this would sort of be a minimum in warping, or this would be a minimum in warping. And so basically what we can say is that we have bands that are strongly warped, and bands that would be less warped. And what we then do is we do band structure calculation to compare basically our results with theory, and to identify which one of those is which. And if we then apply small shifts in the Fermi energy, we can shift those bands down, and we bring the band structure calculation in good agreement with our measurements. And we can basically say on the lithium-ion phosphide, we identify band number 5, which would be an electron pocket, part of band number 2, which would be a hole pocket, part of band number 4, where the other part has a much higher frequency, so a much bigger orbit, and we would need a much bigger mean free path to see that. So there we still have to improve on sample quality. And then we have this very small pocket here. And if we compare that to the arsenide side, we would also predict from band structure calculation that there should be a very small pocket, but we do not observe that. While we observe higher frequencies, which this suggests that this pocket might actually not be there, because otherwise we should be able to observe that. But as well, we have band number 5, band number 2, like we observed over there, and a mixture of band number 5 and band number 2. And with that, another thing we can learn from this then is those frequencies are quite close together, and if you have places like also in the phosphide, you can see here where the shape, the curvature of those lines is very close. We're close to a condition that would be geometrically nested. So now I'm going to basically wrap up what we learned in total from all those values that I just showed you. So, like I said before, we observed higher many-body masses in the lithium-ion arsenide and phosphide, and this leads to a higher renormalization. So if we look at the band masses that we calculate, they're more or less in the same range. But if we look at the effective mass that we get from the measurements, they're quite higher in the lithium-ion arsenide than in the lithium-ion phosphide, which leads to higher renormalization factors compared to band masses. And if we compare this to the critical temperature, this follows this behavior of critical temperature that lithium-ion arsenide has about 18 or 15 Kelvin, and lithium-ion phosphide at about 5 Kelvin. So the coupling is indeed stronger in lithium-ion arsenide. Like I said before, due to the band structure calculation, we suggest that there's a good nesting between the electron and the hole pockets in both materials. And in the lithium-ion phosphide, we have observed, and we suggest 3 hole pockets, while in the lithium-ion arsenide, the central hole pocket is obviously missing. And yeah, so if another thing that we can learn from the renormalization is if we compare band number 2 in the lithium-ion phosphide to band number 2 in the lithium-ion arsenide, which happens that we observe both of them, then we can see that in the lithium-ion phosphide, this renormalization factor is much smaller than the lithium-ion arsenide. So this suggests that there's lower electron-electron or many-body interaction. And if we compare this to the data that was taken on the penetration depth, the calculation that was done by Kanoshimoto and co-workers, then they suggest that the lithium-ion arsenide does not show nodes because of the orbital character, but the orbital character is, of this dxy that they've got here is also observed with slightly less weight on the lithium-ion phosphide. So if we put this together, what we have measured is that the interaction between the hole pockets here in the lithium-ion arsenide and the electron pockets is much higher than the interaction between the hole pocket and the electron pocket of the lithium-ion phosphide. And that together suggests or brings this picture in good agreement why there are nodes forming in the lithium-ion phosphide and not in the lithium-ion arsenide. Thank you very much.
Time for questions?
Yeah.
Maybe 2 questions.
Yeah.
One is when you shift the bands
Yes.
compared to calculation. In principle, that can change the number of carriers, which means that you have to shift electron and hole bands in the opposite direction.
Yes. So this is the main. So if we shift those bands, I'll go back. If we shift those bands, we're very careful that we compare the volume of electrons and holes before we shift the bands and afterwards, and make sure that the Luttinger count, so that the electron count is correct before and after, so that this is in the same range, so that we do not generate hole doping or electron doping.
And the second is an optional question. If you want to comment on your fights with Arcus, you
Well,
can do that, or
I would not say it's a fight, it's a disagreement based on 2 different data sets. So yeah, what the outcome on that is, we'll see.
but so they basically see don't they see a significantly larger area or not?
They do see, so the only thing they comment on is the lithium ion arsenide, and what they see is larger hole pockets. But if you compare the volume of those on the first paper that they published, this would suggest that this material would be hole doped, which is not the case.
Okay.
So I mean, and then we talk about like surface states, which could generate that due to the linkage and height. And but we're measuring bulk here, so we're not sensitive to this surface effect, and we see that this material is actually neutral in terms of electron to hole volume, and they see it's hole doped. So I think we have some pretty good arguments there.
So you think it's a sample problem? You think it's a sample problem?
I think it's a problem due to the surface, which basically, so if you do band structure calculation and you change your Pnictogen height slightly, that can give you different results, right? And if you look at different, if you look at other papers also on the barium 122, it is suggested that the surface would have a different Pnictogen height than the bulk has. Right? And that might explain why their band structure that they see corresponds to their R-test data, but this would not be the bulk, this would only be the surface.
Yes. In your experiments, when you see a frequency, you say I have a number. When you don't see it, can you barely a limitation which is the scattering for the given band? Because we know that in these systems, the scatterings are not the same for all of them.
Yes.
So if you have a band in which you have large scattering, or at which level would you suppress the oscillations?
So the thing is, if we compare the data that we have on those bands, and we argue why we do not see this band, right? If the scattering rate on this one would be about 10 to 20% higher than on those bands, we would already not see it anymore. So that's why we're working on getting cleaner samples, redoing that, and also maybe going to higher fields where basically with the mean-free path, we might be able to have those oscillations grow out of difference. But this is a problem, and this is why usually in most of the materials it takes quite a long time to see quantum oscillations because of the mean-free path, and we're limited by that. And because those two are stoichiometric, it basically was, or we were so lucky to see that quite fast.
So you don't see the red bands in both?
We do not yet see the red bands in those cases. We have slight, on some of those angles, we have slight indication that it's there. But this depends also on the angle. So as you can see, at some points, those bands will cross at higher angles. And this is the Yamachi angle, where basically, if you look at the angle change, you have the maximum and the minimum orbit have the same area, and then they basically add up in oscillations, and you get a higher oscillation amplitude. And this is the angle that you usually try to look at. And in one of the pulses, we seem to be quite close, but we have to redo that and go back, because if you do those measurements at pulse field facilities, you only have a snapshot of 1 week, and you have to live with the data that you get there.
Short question. In heavy filament systems,
Yeah.
I think it's much easier. When people want to know if they have seen all the bands, they compare the ZC, for example, specific pattern from the position with what they measure with THV.
Yeah.
So can you do that?
There is-
Can you do that anytime?
Yeah, so you basically, yes, you can do that, but there's only on the lithium ion arsenide so far data, and that's only one publication where they mention the number. They do not show any data for the Sommerfeld coefficient that we would need for that, and that seems to agree with what we have so far in the mass structure calculation, but there certainly has to be more done on that, especially also on the lithium ion phosphide, where there's no specific heat data yet that I know of. Because the samples are just too small to measure it so far. But yeah, this is certainly something that we try to compare, and that we also compared from the band structure and what they stated, and we come pretty close to that value.
You mentioned also that you wanted to see the change of the effective mass in superrelative state. So could you?
No, what we see is that as TC grows, this renormalization factor is higher, and this explains the higher critical field, or the higher critical temperature of lithium ion arsenide compared to lithium ion phosphide. But you could only see quantum oscillations itself in the superconducting state, if there would be Fermi surfaces that do not take part in this induced activity. And that, well,
Sometimes you are lucky enough that you can
Yeah.
see. So I think we need to